This is the first practicum, so tutorial essentially. And this one is devoted to a brief introduction to R, some in some ideas about the collection of and use of data, and also a brief intro to the topic of solving ODEs in R. So this is what we'll be doing throughout this lecture, practicum, I should say. So to begin with, the R language. So let me make myself smaller. So R is a language that was developed for statistics. It's an open source version of another language called S. It is not so young. It appeared in 1993. It's now in version 4.2 as of very recently, late April 2022. One thing that I will point out, I mean, there's a variety of languages that you can use to solve the type of problems we're looking at here. But I will say one of the things I really grew to like a lot with R is that it's not only a language where you are going to program things out of the box using R language, but it's also quite good at using existing software, and it uses a lot of code that was developed in C, C++, and Fortran. So that's typically code that runs very quickly, and all that R does is provide an interface to some packages that are written in C, C++, or Fortran. And therefore, what you get is the benefit of of a language like R, which is easy to use, is easier to debug than C or Fortran, for example. But you still get the benefit of using this sort of tried and proved languages, these tried and proved languages. And so, for instance, one thing we'll use later on in this practicum is deSolve, which is differential equation solve. So, and if you look at the description of that package, you see that the functions provide an interface to Fortran functions. And C implementations of Runge-Kutta type methods. So this means that R is not doing, they're not reinventing the wheel. These are, ODE pack is a very, it's quite ancient, I should say, set of numerical routines. And what R through deSolve provides is an interface to this. Okay. Another aspect that I think is quite important with R, but that the same is true about Python, I should point out, it's that it's a very active community. So if you're looking for answers, you will typically find them easily on the web. And that makes for a very convenient approach, because of course that means you can easily find information. Now there's a variety of development environments for R, going from the most unfriendly to friendlier versions. There's a terminal version. When you install R, you have access to a terminal version, but that is not a very friendly environment. There's a slightly nicer terminal that I discovered recently. I've linked it here. It's called Radeon. You can evaluate scripts online, and on the command line, like a Unix or Mac or Windows command line. And I will point out that this is very, very useful in a variety of contexts. I will illustrate later. And finally, there's a bunch of IDEs, so integrated development environments, the most well-known of which being RStudio, which is what I will use later to show you some code. RKWARD is useful, in particular if you're running Raspberry Pis or some Chromebooks that that have ARM processors and for which RStudio is not compiling versions, because Macs now have ARM processors, but RStudio compiles a version for ARM, which they don't for ARM on Raspberry Pis and so on. And I'll point out that it's also possible to integrate R into Jupyter notebooks. So if you don't know what that is, it's not really important to look at. But if you know what a Jupyter notebook is, just be aware that you can write a Jupyter notebook in R as well as in Python or Jupyter, which is the sort of base thing that you would be doing. To go a bit further, there's even more evolved programs linked to R that I might mention briefly. I will show you some examples of some of them. So I will just point out that RStudio, that environment that I'm going to show you later, has a server version, which allows you, if you have a Linux server, to run RStudio and serve it on the web, which is very convenient. So for example, for me with a Chromebook, I can connect to a server that runs RStudio and do my work as if I were on the server instead of being on my Chromebook. Shiny is there is an example, and I will show you Shiny later. There is an example in the lecture about stochastic systems where I'm playing with sliders to change the distribution, well, the look of the distribution that you get when doing Erlang distributions. So I think that's lecture 6. If you want to check, this is a Shiny application, and it's actually running on a Shiny server rather than on the computer, as I will show you later. Okay, and Shiny server is a bit like RStudio server. It allows you to run Shiny applications on a remote Linux box. R Markdown, I will show you an example of. Markdown is what I'm using, for example, to produce these slides, but you can run Markdown within R, and that allows you to evaluate commands as you're producing them, and that's very useful to generate a report in HTML or PDF. And you can make slides. I will be showing you a bit later how to do that. And finally, RSweave is LaTeX incorporating R commands rather than Markdown incorporating R commands. This is very useful for reports. I would say that nowadays that R Markdown has become much more prevalent. RSweave is not used as much, but it is. It allows you to generate very nice looking PDF through LaTeX. The advantage of R Markdown over this is that you can generate PDFs mainly using LaTeX, but you can also generate HTML code. Okay. So in terms of what R does, or how it works rather, it's a scripted language. So that means it's interactive. When you are in an R command window, you can run the command, evaluate it, it returns an output, and you can work with this output right away, etc. So this allows you to run in real time. But, and this is a remark that I made earlier when I said R scripts were useful, running R script, because when you're running interactively like this, sometimes you tend to forget what you've already done, and like if you're just doing 2 or 3 computations, it's fine to work interactively. But if you're going to reproduce your computations later, you have to be very careful, because some of the times when you're running things in a script, so you're writing down all the instructions that you want to execute sequentially. Sometimes if you, on the other hand, decide to do a little computation on the side and modify a variable with that computation, if you don't write it down, it will work in the current context, in the current R session, but it would not work when you try to run it again if you've forgotten to write down what you've done. And that's why I often recommend, if you have complex code, it's really good to run it through R script from the system command line, so from the Unix, Mac or Windows command line, rather than in an R command window. Because when you do that running from as an R script, it evaluates the entire script without having anything resident in memory. So if your script runs when you run it through R script, you know it's going to run every time. Whereas if you just run it from the RStudio window, for instance, and do some editing, you might run into trouble. Now, in terms of programming, let me, I'm not going to give you a lot on programming in R. There are many resources about this, but let me give a brief rundown on some of the ideas that I think are the most important. So first of all, a lot of people have programmed using MATLAB. So just a remark for those who would be coming from a MATLAB world. This is very similar to MATLAB, with, of course, enough differences that are going to annoy you and will require some adaptation. But once you've dealt with several languages, MATLAB, Python, R, Octave and MATLAB are very similar, but anyway, all of those languages are roughly the same with some differences. So one important thing is that R does assignment of values to variables in two ways. So you have this classical way where you want to say, let me assign the value 10 to the variable x, but there's also something that looks more like what you do in formal algorithmics for assignment, which in algorithmics, that's how we denote assignment. But so you're able to do it that way. I'll point out that R purists tend to favor this. I don't really care. I use both independently. Typically, if you see this in some of my code, it means I've copied it from somewhere because I tend to use X if I don't think about it. But I understand why purists want to use this assignment statement. I just don't really subscribe to the reasons why. Lists. So lists are very important in R. So if you're coming from the C / MATLAB, etc. environments, lists are the sort of equivalent of structures in C, although they're more flexible in the sense that they don't require you to define a data structure before you use it. So you create an empty list by just passing this function, and then you populate the list by indicating that here the entry A in the list takes the value 10, the entry B in the list takes the value 3, the entry another name, because you can have whatever you want as indices to your list, takes the value ploof ploof, for example. And then you can address list entries by just referring to their position. So if you do so, what you get is, so this says in the first position is an element whose name is A and whose value is 10. If you use a double square bracket, then you just get the value of the second entry in the list. You can also refer to the entries in the list by using that operator dollar, and which tells you what the value of A is here. You can use strings, okay, because those names are strings, and so you can use strings, or you can use this, okay. Vectors are essentially like vectors in MATLAB. So for instance, if you want to create the vector x with entries from 1 to 10, you would do so like this. There's a very nice operator which is C, which makes lists of vectors. And so here what I'm saying is in the vector y, I want to add the vector x, which I just created, and the value 12. And so when I look at y, I now have the numbers from 1 to 10 and the value 12. If I create a vector with entries red and blue, I get red and blue. And if I were to add some entry to this vector, it would be the chain, the string 1, okay, the character, but here, I mean, typically a chain, because vectors and matrices, that's the same for matrices, can only have one type of entry. A list can mix entries of all types, but here, because I've started out putting strings, well, the entry that I am adding is considered to be a string. Matrices of vectors, you can create a matrix of zeros by using this command, mat_vec, and then indicate the number of rows and number of columns. Or you can make a matrix by prescribing the entries. So here I'm saying, well, the entries are 1, 2, 3, 4, and this is a matrix with 2 rows and 2 columns. And so I get this matrix. And be careful. You see 1, 2, 3, 4 are like MATLAB actually, but works columns by columns, not rows by rows by default. So a matrix is just a very long column vector. So that means that entering 1, 2, 3, 4 means you get 1, 2, 3, 4. If you want to indicate that things are entered by row, you say by row equals true. And I should point out true is a reserved keyword that means true. So if you want to indicate that something is true, you could specify it that way. And yes, a remark, R uses arguments, functions in R uses arguments, and one of them, so typically there's an order in which they come, but I always recommend being as verbose as possible, because I mean, if I remember well, like matrices or vectors, for example, have, if you're looking at a matrix with prescribed entries like this one, the arguments are data, number of rows, number of columns. But you can put things in any order, provided you remember to say that, for example, NR is equal to 2. You could call it after NC equals to 2. Or for instance, here by row equals true, you could put just after the matrix. It doesn't matter, provided you use the naming of arguments. Matrix operations. So there's a very interesting, let me make it myself bigger. There's a very interesting issue when you're doing matrix computations in R, which, for instance, I end up doing a lot of, is that contrary to most other languages that I know, R uses the notation star to denote what is called the Hadamard product, which is the entry by entry product of matrices. So for instance, if you come from the MATLAB world, that star that R uses would be A dot star B in MATLAB. So that's not the standard multiplication. If you want the standard matrix multiplication, you have to surround the star by 2 percentage signs, one on each side. Okay, so this is the proper matrix product of A and B. This is the Adama matrix product of A and B. It is slightly annoying at times. It is I point this out because it is a source of error. Vector operations, let me just point out that there's also a frustrating thing. If I have a vector from 1 to 10, as before, then if I add 1 to this vector, of course, this is not a properly defined operation, and so different languages will do different things. In R, adding a scalar to a vector means that you're adding a vector of 1s of the same length as x to each entry of x. Okay, so you're shifting x plus 1 is simply x plus the vector with 1 10 times, and so it is this vector here. I point this out also because this is another source of errors. When, for instance, you found an entry position and you want to say that you want to go to the next entry position, you have to remember that sometimes you need to use parentheses in your call to the arguments of a vector, because otherwise you end up shifting things instead of shifting an index. For those of you who come from MATLAB, there's no keyword end. That was one of my biggest frustrations when I started using R. There's no end to access the last entry. So typically, if you have a list of vectors, you can use length of the vector. So if you want the last entry in this vector x, for example, you would say x of, with square brackets, length of x, and that would give you 10 here or 11 here. Ncar is going to give you the number of characters in a chain, in a string. Dim for matrices is going to give you the dimension. I should point out there's also 2 functions, nrow and ncol, that gives you the number of rows and the number of columns. Dim gives you both dimensions, and so you would say dim of 1 or dim of 2 to indicate rows or columns, but otherwise you can do nrow, ncol. Flow control is very classic. The condition that you want to check if it's true or not comes between parentheses. So it's always between parentheses. So if whatever condition and what's between the parentheses needs to evaluate to true or false. So if that condition is true, then whatever you're executing afterwards is done. I will point out that it is you can forfeit the curly braces if there's a single instruction, but I really recommend against doing this. Just use the curly braces even if you're doing just one thing, because when you get into else statements, that leads to confusion over time. And by the way, so else statements can be used with an if. So you can have an if, else if, etc. And the last one would be else, or you can have just an if and else. Okay, but so this is how things work. For loops applies to list or vectors. That's quite useful. So you can have, when I write for I in 1 to 10 here, what R understands is for I in the vector that contains the entries from 1 to 10. Okay, so you can, for instance, create a very not very, but here create a discrepant index. So here, instead of running from 1 to 4, I can run from 1 3 and 4, or you can loop on strings or whatever. Like if my vector has entries truc, mush, and chose, then n here would take the value truc first and mush later and then chose. Or you can also use lists, and what's in the list doesn't really matter. Okay, so here the list, remember I said lists can have they can mix entry types, and here I would loop on something that is a string or a number. That doesn't matter. One remark, one point that I think is really interesting to spend some time on, and I'll come back to this later, is the function lapply. And there's other functions. There's sapply, vapply, mapply, and a variety of others. These are very interesting functions to learn how to use. Typically, well, the basis is that lapply applies a prescribed function to each entry in a list or a vector, or for some others for a matrix. And one of the reasons why I really stress that it's important to learn how to use them lapply is that there is a parallel version that I will illustrate later in the course, which allows you to do, when you have a problem that is embarrassingly parallel, so I'll come back to this, when you have a problem that you can run as a parallel loop, then you can use lapply with great advantage. Okay, so here, for example, I'm showing you how you would use lapply in a very simple case. So here I'm making a list of entries, and in each list element, so L will have entries 1, 2, etc. I am going to make run if. So this is runif, it's not runif. Runif is the uniform distribution of I entries. So what that means is that the list L has the first entry one random number between 0 and 1. By default, if you don't specify the bounds, the uniform distribution is between 0 and 1. The second entry has 2 random numbers between 0 and 1. The third entry has 3, and so on and so forth until 10. And then what I can do is I can lapply, so apply to this list L that I've just made. So this is the argument, so this is what list, and I'm saying the list is L. And I can apply a function, and here the function that I'm taking is simply the mean. So what that is going to do is it's going to compute the mean of each list entry. Okay. And if I want to make a vector, I could, for instance, unlist the result, or I could use sapply instead of lapply, which will return a vector like this. And so what we will get when we run this, and I'll show you very briefly later, when we run this, is the mean of the numbers, the sequences of 1 to 10 uniformly distributed random numbers between 0 and 1. lapply can be made to work more complex lists by, for instance, define even online, but then sometimes the function that you'll define will be even more complicated than this. But here, for instance, let me show you what I'm doing. I am using that. This is what's called a local definition of a function. So this is a function that I'm just defining for the time that I'm using sapply for, which is lapply. Okay, remember, it just is going to give me a vector directly rather than a list. So here I'm making a list, and what I'm saying is that each entry in the list is actually a list itself. So this is a list of lists, and these lists that I'm making The first one is like the one I was making before, but I'm calling this sublist A. So L of $1 is a list that has I uniformly distributed random numbers between 0 and 1. And the second list entry for each list and the second list entry for each list sublist. Sorry, I'm getting confused with the level of detail. Is a list of random numbers, but this time it's 2I. So the first one has 2 entries, the second one has 4 random entries, the third one has 6, and so on and so forth. And here, what I'm doing is I'm applying to this list L that I've just defined this function. So this one I have to make up as I have here, because that list has entries that are a bit more complicated than the ones before. And what this is saying is that for each x, and x is L of 1, L of 2, L of 3, etc. Okay, so x is the sublist that has the entries in L. Okay. So for each one of them, I'm going to return the length of the entry B for that thing. And so before we look at the result, you can expect what we expect here is that for I equals 1, I have a length of 2 because I have a vector with 2 random numbers. For I is 2, I have 4, and so on and so forth. And when you run it, you indeed get those numbers. Okay. It takes a little while to get around to sort of using lapply or sapply, etc. Easily, but once you manage to do so, it's a very, very useful way of thinking about the problems. Let me show you an illustration in a sense. So suppose, and that also brings me to a very useful notation here. So suppose that I want to vary 3 parameters. So the way you've probably done it up to now is that you will have a loop for parameter 1. And so here I'm taking, for instance, a parameter 1 that's varying so this is sequence from 1 to 10 with 10 entries. Okay. Parameter 2 would be a sequence from 0 to 1 with 10 entries, and a P3 would be a sequence from -1 to 1 with 10 entries. Okay. If you're doing this classically, let's say, what you will typically do is a for loop for this one, in which you will put a for loop for this, and then a for loop for this. Okay, 3 imbricated for loops, and inside of that you will compute a value. So I want to show you another way to do this, which is very useful because it combines and makes it possible to use parallel apply on these type of things. It's to use the function expand grid. So expand grid, what it takes is it takes each one of the parameters that you have here, and it takes every single value. Okay, so it's going to take the value 1, and then every single value of this, and then every single value of this. So what it's going to make is a matrix that has, well, in this case, 10 times 10 times 10 entries, and where the first column will be the individual variations of P1, and it goes from the rightmost to the leftmost. So the first column will have 1, 1, 1, 1, 1 several times. The second column will have 0, 0, 0. And the third column will have -1, -1 plus, well, I want 10 of them, so it will be -0.8, -0.6, etc. And then when it gets to 1, it will loop back to -1, but this time with this second index being 0.1, this second value being 0.1, and so on and so forth. This way you get a matrix where you have all possible variations of this. And you can, for instance, store them in a list. Once you've stored them in a list, then you can take this and apply and use lapply on this, or more importantly, use parallel apply. Because if you can use parallel apply, and I'll come back to parallel apply later, if you can use a parallel version of lapply, that means if you have, say, like the machine I'm recording this on has 128 cores, on a parallel apply, I can run 128 different rows in that matrix at the same time. Okay. Now, let me move on to the second part of this practicum, which is dealing with data. And I'm going to discuss a few points quickly. Again, this is something where I recommend getting your hands dirty more than anything else. And I should point out that the code, some of the code that you see here is available online, okay, in the repo. I'll point out there's a paper that I wrote some time back, so it's a little annoying. I'll try to get it up because they made something which is really annoying. They converted the code to images. So that means you can't select, when you select, you're not selecting the text. But I'll point out that there is a online version of this, which you should find if you have a PDF somewhere. There's a link, yes, here. No, that's all marked down. That's not what I want. Here. There's a GitHub here, and this contains the proper code. Okay. So if you want to play with this, there are some notions in here that go much further than what I'm discussing in this lecture. So this is something I already discussed, so I'm not going to spend a lot of time here, but I really advocate for being data aware. Okay. It has become very, very easy using R, but also Python or other languages, but like the main ones would be R or Python. It's become super easy to grab some data, not all data, but some data from the web using open data sources. And there's a lot of places that now have an open data policy. So, and I'll repeat what I've already said, I don't think it's necessary to always have data permeating your work, but it is good to really be aware of the context in which you work. And in particular, if you're thinking about, sorry, that was a weird beep. If you're thinking about, like working in public health or epidemiology, like practical epidemiology, then you can't abstract yourself from the data. It's good to know where it is. And so in terms of data, there's several types of data. There's what we typically call closed data, as opposed to open data. It's generated by a variety of entities, typically companies, governments, or research laboratories. And when you have access to it, if you do, it's typically in a way that has multiple restrictions. Okay. Whereas open data is typically often actually generated by the same entities, but it is liberated. So it is freely usable. And in particular, governments have started to do this quite a lot. I will point out that there are some limitations, of course. There's a wide variety of licenses. So beware that even if the data is open, it doesn't mean you can use it to do anything. So you always have to look at the type of licensing that comes with the data that you're acquiring. And there's also the fact that it's open means that there's a wide variety of qualities. So you need to be aware of this. It is not uniformly good data. The data is only as good as the people that collect it make it to be. And so you shouldn't think that everything that you get from as data is equivalent. Okay. I'll point out these are some examples. So open data initiatives. There's a lot of governments that range from the local to a much higher level that have created portals, and those portals centralize data. So I'll give you an example. This is the open data portal for the city of Winnipeg, for instance, where I'm located. And you can see that there's a variety of data sources that you can access from this web portal. Let me show you another one. That, for example, the Government of Canada has an open data portal from which you can get a variety of data sets. So, for example, I could look at education and training, and you can see there's a bunch of data sets. So typically, you have to check because often the data is relative to a certain period in time, or it might be very partial, or etc. It often is, for example, look, this is a 2013 graduate survey. Things vary a lot, okay? But a lot of that data is accessible. And I'll point out one that I'm going to use in a second is the World Bank. So they have an open data and they have a lot of indicators. I don't remember how many, but I think it's close to 20,000 different data sets that you can access. The WHO has a data initiative. So all of those places have data online that you can access, and typically you can access easily. So let me discuss this just a little bit. So if you're gathering data, so sometimes the worst case scenario is you do it by hand. There are examples. There's 2 data sets that I added to the repo in the data subdirectory that are data sets that I assembled by hand from data that was accessible online but needed to be gathered by hand, essentially. But you can also use programs that allow you to click at the data points. So once a paper is published, in a sense, the data that it contains becomes public domain data, but they might not give you the actual data set. But if you want to roughly match what data they have, there are programs like those that allow you to, given a figure, essentially with data points, get a list of data values. Using APIs, so these are interfaces to websites, typically. I'm not going to detail this because what I'm going to look at mostly here is the use of R packages, but those R or Python packages that, well, I'll give you an example of an R package, and what it does is it interacts with the API. Okay, so that's what most of the R packages that are around that allow you to query data, that's what they do. They provide an interface to the APIs because the APIs are sometimes a little difficult to program at first, whereas with those interfaces, it's very easy. And I'll show you an example in very little time right now. So let me show you how quickly you can gather some data. And that's really my point about being data aware is made with that one little slide. So this here is a library that WBStats is for World Bank stats. So it's an R library that interfaces with the World Bank site that I was showing you earlier and allows you to query the API for the World Bank. in a way that is quite easy. And so here, what I'm doing takes this single line, well, double line here, but to do this, it's very, very simple. I want to get the population of South Africa, which has a 3-digit ISO code ZAF. And I want this indicator, which is the total population. Okay, and you need to look to search a little bit in the database to find those things. There's tools in the WBStats package that actually allow you to do that. Here I've already searched for an indicator, and I'm happy that this is the indicator that I want to use. This is going to give me the total population of the country that I choose. And I could choose, if I don't say what country, I can get all of the countries for which they have data. What I'm saying here is give me the most recent 100 values. So it might not have 100 values, but I'm saying, well, okay, go as far as 100 if you can. And this is simply because I prefer the way the data used to be returned for a single indicator. So don't worry too much about this. What this means is that the value you get back will be in the column value. Okay. If you don't specify return wide equals false, which is the default is true, it returns the things, and in that case, the value will be in a column that has the name of the indicator as name. But I prefer value because value is shared across all indicators, but that's just personal preference. And so this line by itself returns the population of South Africa over whatever length of data they have. All of this here has nothing to do with getting the data. It's simply me plotting it. Okay. So I'm using a little function that I've made available in the repo that actually formats the y-axis in a way that's a bit more easy to read. And then I'm saying that the output must go to a PNG file, so a figure file. And then once the plotting is done, I want to make the PNG file. I want to crop the figure so that the empty spaces around it are removed. Okay, but getting the data itself is just this command. And what I get is this. So this is the population in million from 1960. So that's the first, oops, I should move myself out of the way. That's the first data point they have on that World Bank indicator for South Africa. And so we've got 60 years worth of population. And that's showing me how the population of South Africa changed over that period. Okay. So again, just this. It's very easy to get this information. Okay. Let me show you a slightly more evolved example that I'm not going to spend too much time on, which is a work that I did in Winnipeg about Dutch elm disease. So Dutch elm disease is a fungal disease of elms, so trees. This is not human epidemiology, it's tree epidemiology. And it's caused by a fungus, and it's transmitted by the elm bark beetle. So it's an interesting life cycle, a very complicated life cycle. But essentially what happens is that the beetles get in the trees, they dig little tunnels, that's where they spend the winter, and then they exit the trees, they fly to other trees to eat the canopy. And what happens is if they're in an infected tree, when they leave the tunnels, they carry the fungus on them. They're not infected themselves by the fungus, they have it on themselves, and when they get to a new tree, if the tree is unlucky, the fungus infects the new tree. And this is really a problem in North America. A lot of places had resident urban forests of elms, and most places have seen them decimated because of Dutch elm disease. In Winnipeg, we still have a few, and so the project consisted in trying to study this. So this I've showed you earlier. This is the open data portal, but when you dig down into it, there is a data set that is the trees of the city. And this data set is humongous. So this is a map of the city of Winnipeg. And what the city has done is they've inventoried every tree that's on public domain in the city. And they've indicated, you can see here, these are the first few lines in database. So they have a botanical name, they have an ID for the tree, they have a botanical name for the tree, they have a common name, they say what electoral district it's in, what neighborhood it is in, what's the diameter at breast height. That's the way they evaluate tree size. Essentially, is they look at diameter at a certain height, which they call breast height. There's a standard for this. Whether it's where is it located? So when they say boulevard, it's the trees that are next to the road in North America. You know, like you have the road, then you have a row of trees, then you have a sidewalk, and you have people's front lawns, and so that's what they call a boulevard tree. And whether the property is public or private, it could also be a park, etc. Plus, there's the individual GPS location of each of those trees. So they are indicated in two different ways, but you have that information. And so, for instance, I live somewhere here, and this is sort of a neighborhood in which I live, and you can see the trees there, etc. The idea that we had there was to use this and try to see if we could do a model of Dutch elm disease spread. So to get the data, and I'm sorry the whole line is not available there, but in it doesn't really matter. I think it's on one of the examples I have, I'm not sure. But if you are to read this data, yes, I know it's in the RMD file. Okay, I'll come back to this. So if you evaluate this command, what you do is you read from this web address. So if you have a CSV file, so that's a comma separated value file, all you need to do to get the data from the web into your machine is this command. So it's very simple. And when you do so, for instance, when I did that slide, it's changed now. Of course, it changes over time. There were 300,000 trees in the database. Then we're only interested in elms, and actually in American elms, and so we select American elms. Okay, we find the indices. GREP is the usual GREP, and I find the indices of trees whose common name is American elm. I'm saying, yeah, ignore the case, because in case they've written elm with a little e, for example, then this will ignore the fact that there's a case. And then I just select this, and I'm left with 54,000 elms. Now, the disease dynamics is complicated, as I said. It involves trying to figure out what the dynamics of the beetles is and how this interacts with the trees. So I'm going to skip this quickly. I'll just point out it also is temperature dependent, and what you're seeing here is data that we pulled off this time Environment Canada. So this is I think all the daily temperatures, all the average temperature over a day, so daily in that sense, daily temperature in Winnipeg over the last 30 or 40 years. This is also data that's available for free online. And what's important for us is that the process itself is governed by this temperature a bit. because the beetles do certain activities, breeding, emerging from the trees and so on, when certain temperature conditions are satisfied. And now let me show you what I think is quite a cool application, and again shows you what you can do with data. So there's two modes of propagation. I was of Dutch elm disease. I mentioned the fact that Dutch elm disease is spread by beetles, but there's another means of propagation, which is in that case almost automatic. If you have two nearby trees whose roots systems, so at some point the roots touch and one of the trees is infected, almost automatically the touching tree is also infected. And the size of the root system of a tree, of course, depends on the size of the tree. But there's a way to sort of recuperate an approximation of the extent of the root system based on the height of the tree. And once you have the diameter at breast height, you can approximate the height of a tree. But there's an additional constraint. It's that the way the roads are built means that if trees are like, I was talking earlier about boulevard trees, so trees that line a road, if they're on the same side of a road, they can touch. But if they're on opposite sides of a road, they cannot touch, because the way the digging goes to make the roadway forbids roots from going underneath. Okay. So if trees are on both sides of the street, they cannot touch. So they cannot, if one is infected, it cannot propagate directly to the other. And so we wanted to make a model that, a simulation model that would allow us to look at these interactions. And to do so, we thought, okay, we have a location of 50,000 trees. We're going to look at this, but we also need to be able to say there's no interaction. So how do you do that? It's actually quite simple. It's demanding, as I pointed out in the previous slide, it's demanding in terms of computer power, so to speak, computer memory, but it's easy to do. So one thing we can do, so we can first say, well, trees that are more than 100 meters apart or even less than that are not going to have their roots touch. So we are first going to prune. We've got about 50,000 trees. We compute the distance because we've got all the locations. We compute all the distances between all pairs of trees. And whenever that distance is more than some threshold, yes, here we did 50 meters. Whenever that distance is is more than some threshold, we discard this as a possible interaction. And so we only keep the pairs of trees that are less than 50 meters away. Okay. Then what we do is, and this is okay, this is annoying code, but if you need for something like this is how you could do it. I'm looking at all pairs of trees, and I want to make line segments between all pairs of trees. So I look at all the origins, let's say one tree in the pair, all the destinations in the pairs of trees. Remember, the trees that are closer than 50 meters. And what I do is I use this code to make line segments between all pairs of trees. Okay. Once I have this, I then use this package, which is for OpenStreetMap data. So if you don't know OpenStreetMap, it's a fantastic open source initiative, which essentially has, it's a bit like Google Maps, except that it's truly open source. And it's for essentially every place on Earth is mapped. So some have more information than others, but for those where the information is available, it goes down to a level of, if there's a fire hydrant somewhere, sometimes it's indicated. So you know if it's a road, if it's a parking lot, if it's some basic structure. They have house houses, locations in some places, etc. So OpenStreetMap is a fantastic resource and you can query it. So here what I'm saying is, okay, get the bounding box for Winnipeg. So I'm going to extract a box which contains the place on the map which has Winnipeg. And in that bounding box, I am going to get highways. And in the case of a city, it's residential highways. So these are streets, bigger streets, etc. It goes down to the level of a residential street. And I trim the data to only keep those that are in the bounding box. I get the rivers as well, because the rivers are also not crossable by routes. I could get the train tracks. I think I actually have in the proper work that we did. But so we get a collection of roads. And then all we need to do is we have these line segments that represent pairs of trees that are potentially in contact. And then we have the roads as lines, line segments, a series of line segments. And all we need to do is we need to check if there's an intersection between a pair of trees and a road. If there is, the pair of trees is on both sides of the road, and therefore they're not connected through routes. Or if there isn't, well, they are on the same side of a road and they can be connected. And this is simply done by looking for intersections. So this simple, very simple command here looks for intersections between tree pairs that I've just made here and roads. Okay. And once you do that, well, of course, you prune things a little bit and you get, so this is difficult to see at this level, I'm afraid. But you can sort of figure it out here. So here, for instance, where my mouse is, you can see that these are all the trees, okay? And what you can see is that I'm keeping some trees on both sides of what is a road. Or here, you can see that there's intersections here, and I'm keeping trees on the same side of the intersection, and I'm considering them as disjoint from the other side of the intersection, okay? And this is what we use to then model the spread. Okay, so this is just to show, and as you can see, it's not a lot of code. I mean, it took me some time to get the code running. I won't lie about this. It wasn't a very easy thing to do, but quite quickly, and with a decent computer because of the memory requirements, we have this very nice setup in which we can then do modeling, I mean, a simulation of spread. About data, one last thing I want to mention is that, so data wrangling is the practice of making data into a form that is usable, essentially for the purpose of either illustration or use in models and so on. And I'll just point out a sort of recent trend in R, which is the use of deployer and more generally what is called the tidyverse. I'm more old school. I tend to, I worked for years with data sets using MySQL. So this is a database programming language. And so because I know that language quite well after those years, I tend to stick with SQL, but deployer is a very good option as well. I'll just point out SQLDF. Sorry, interruption by camera. So SQLDF is SQL on data frames. So what it allows you to do is treat a data frame as if it were a table in SQL. And deployer, as I said, is part of the tidyverse, and it allows you in particular to use what's called the pipe, which I'll illustrate in a second. So let me very briefly do something. This is a data set that I included in the data in the data folder. It's data that I put together about the SARS-CoV-1 epidemic, so 2003. So here, as I indicated, if you want to read from a file or from a web, it doesn't matter. You could simply do it by read CSV. This is a CSV file, so you would use read CSV. And I've loaded SQLDF and deployer. I'm loading this file and I want to plot the evolution of a number of cases in Canada, say. So I'm selecting my country as Canada here that I will use later. So one of the basic ways, I mean, there's several ways to do this. One of the ways I could do to select the data for Canada would be to say, well, I'm going to keep aside the indices where the country, so that table that I load has one column that is called country and has the country written in full. So this command says which indices in that matrix data frame have country equals to country that I've set to be Canada. So this is Canada. And then I could say, well, this new table that I want to do is going to be the table that I have where I'm only keeping the rows that have this index that I've selected. And of course, I could do that directly by putting this command into here. Okay. In SQLDF, what I would do is the same thing, except that I would use the command SQLDF. And here I could either write it by hand, but if I want to be able to change this, I would simply make a string. And that string is the query, and it's going to say select star. So that's all the rows, all the columns from the table source, which is that one I read, where the country is equal to, and I just print the country here. So that means the country is Canada. And in deployer, I would use the pipe and I would say, well, that selection that I want, I'm going to select in source those that filter, okay, filter being keep those that satisfy a certain criterion. And here the criterion is that country, so the column country in the table source has value CTRY, so Canada. The three ways give me the same thing, which is a table that has by date the number of cases in Canada. Now, one thing that I need to do is, the data has the cumulative number of cases, and if I want to plot the incidence, then what I need to do is I need to subtract to do the difference between values, okay? Because if one day I have 18 and the next day I have 20, then this means that the second day I had 2 new cases, and that's what I want, the 2 new cases, not the cumulative number. So for this, I can use that function, diff, which does the term by term difference. The only thing is when you do diff, of course, the first one doesn't work. It has one less entry because you're taking one by one differences. It has one less entry than the original vector. And so what I'm doing is I'm adding a 0 at the beginning because it's the 0th entry. It does difference between entry I and entry I minus 1. So the 0th entry, the first entry disappears, and so that's why I put a 0. Okay, so I'm just adding a column to my table, source selected, and that column is called incidence, and it has the difference between the number of cases. But now, the way the data is reported in this particular instance is not when there is a change. The way the WHO was reporting the SARS cases at the time was a little confusing. And so, for instance, they would have several days where the cumulative number for Canada would not change because they were just listing all the places that had SARS cases. If there was no change, then they still listed it with the latest value. That means there's when you do this computation with a difference, there's quite a few rows where the incidence is 0. So and there's actually negative adjustments, because if they were doing a correction, then they subtracted one case. But I'm discarding those. And what I'm saying is, again, so this is using the pipe deployer. And I'm saying, okay, keep in source selected those whose incidence, the column incidence, is positive. And to plot the result, I'm using a package that's called EpiCurve, which I didn't include here. I should have included in the libraries. It's another library. And before plotting, I also actually need to make sure that the date is in proper format. So I'm using another library called LubriDate, which is also part of the tidyverse universe. And that allows you to format dates very easily. So this is simply saying that the toDate column is actually a proper date. And this is a so if you look at the column in the data, it's in the format year, month, day, but it's not really well, I mean, it's not recognized as a date. And here, by using this function, I'm making it clear that this is a date, not a random string character chain, okay? And then this function simply says, take the data set source selected, use this for the date, use a period of 1 day, and plot incidence, which is that column that I just created. And what you get is a plot like this, which is the type of plots we've discussed before. And you can see this is SARS-CoV incidence in Canada. I should have said in 2003. So this is March 2003 down to July 2003. And these are the several waves that we saw in Canada. This is probably not the most accurate data because it's derived from, as I pointed out, from a WHO website that was updated daily and is subject to some corrections and so on. And I think there's much better, if you're looking for the data in Canada, there's probably a better source, but that's to give you an idea. Now, the last thing I want to do in this lecture, practicum, I should say, is to show you how to solve ODEs numerically. And I will do so by first talking a little bit about the deSolve library that I'll be using. And then I'll talk a little bit about fitting data, because I think it's an important part of the work, and explain this here. So first of all, the deSolve library, I pointed this out already, that deSolve is an interface to pre-existing numerical software. Okay, so this is Fortran and C, which means it's really fast. ODE pack, I mean, the one that they're interfacing to in Fortran is actually from Lawrence Livermore National Laboratory, who is really, really good for numerical analysis software. And these were developed in Fortran 77. So that gives you an idea of when this started to be developed. So this is really code that has been existing in existence for quite some time. There's other good solvers that are included. There's some written in C. There's actually, I should point out, you also can, even if, for instance, you want to implement your own numerical routines to solve your problems, you can use deSolve to interface with some code that you have made. The numerical analysis package, suppose you want to do an RK8 or a Runge-Kutta, this is 8 steps, I don't know, some crazy thing. Well, you could do it. Okay. So let me very briefly illustrate how things would work. You need to call the library. As with like virtually all numerical solvers for ODEs, what you do is you define a right-hand side that depends potentially on time. If your function is not, your right-hand side is non-autonomous. It depends on the state, x, and it depends potentially, and it will depend for me, on parameters. And here I'm writing a logistic function. So one thing that I could do is with as list, this means that I can use whatever is passed as an argument. So you see here, let me go to this directly to explain. Here I'm saying the initial condition is a named list, essentially named vector, where n is equal to 50. So what that means is when I pass this initial condition, it knows one of the variables is called n. And so when I use with as list, it gets in x n. And so the n here, I don't have to say n is equal to x of 1. Okay, automatically with this formulation, with a named variable here in the initial condition and the as list here, that n is tracked down to that initial condition. Okay, and if you have more, and you'll see that in a second, if you have more, then it works with more as well. You need to specify parameters, and the same way I'm specifying them as a list here. The times at which the solution is returned, that's important. So those of you coming from MATLAB, you typically specify the starting point and the end point in time. In deSolve, you specify the points at which the solution is returned. It's not necessarily where the solution is evaluated. Okay, the method that you're using, there can be several methods, but the methods that you're using might select different integration points, but they will return the value at the times you specify, which is very convenient for what we will do later. And then you simply need to call ODE by default. So that's not changing anything, okay? ODE with the initial conditions, the times, the function that defines the right-hand side of your differential equation, and whatever parameters you are listing. And let me point out, so here you can see that I've passed P as a parameter list, and that I'm using $r to access this, and $k to access this. Let me just point out that you can even be more, if you don't have too many names, too many different names, and in particular, if you don't have any names that match in your state variables and in your parameters, you can add P to a list of arguments of that list. So in that previous slide, I was using X as in the as list statement. Here I'm using X and P, which means that I don't need to do $, because it knows that the list P contains an entry R and an entry K, and so it knows to use them here. Okay, this is exactly the same as before, except that it's a little simpler because it doesn't have a $. Okay, everything is the same. I'll point out the default method is what's called LSODA. LSODA is interesting because it switches automatically between stiff and non-stiff methods. So if it detects that the problem is stiff, then it moves into a stiff method, and if it detects that the problem is non-stiff, it moves to non-stiff. And that is true because problems sometimes will be stiff for some parameter values and not elsewhere, and it will detect this as you're going. So the method might change during the execution, but there's a lot of other methods that you can use. Okay, these are the ones, if you're coming from MATLAB, these are functions that work like the ones in MATLAB. There is a variety of things. I'm not going into details. There's even this one, iteration, which is for discrete time systems. So you can have a discrete time system and use this. And as I pointed out before, you can even implement your own method. So you could devise something that would be called ODE 8.7 or something like this, or 7.8. If you wrote the code and did so in a way that functions with deSolve, then you'd be able to use it as a method. And now the last example that I want to look at, and that I'll look at a little bit with an R session running later, is fitting data. But before I start, let me explain what this is about. So, and I'll point out to start with that this is a super simplified version of what you end up doing. There's way more elaborate stuff. So there's a nice little course by Rhoda on Bayesian inference for dynamical systems. That's one way of approaching things. There's a good primer by Porté on using, for example, the Akaike information criterion. So you have links to these two papers here. So model selection is where you look at more than one model. You write a collection of putative models for your process, and then you look at which fits the best, and that's another way of doing things. So what I'll do here, I'm going to illustrate fitting by grabbing some epidemiological data online, and I'm going to try to fit an SIR model to it. And this is the baby version, so I don't guarantee anything. And I'll point out another paper of Rhoda with collaborators, which was written about COVID, but this is a common problem in epidemiology, is we have an issue with what is called identifiability of parameters. I'm not going to go into details. It simply says that when you're trying to do a fitting, there might be many points in parameter space that minimize your objective function. Okay, so, and that means that 2 points that give you the same minimum for the objective function might give very different regimes. Okay, so this is what's called an identifiability problem. This is a good thing to keep in mind, and so I really recommend reading this paper as well. So what's the general principle of a fitting or an identification problem? There's a variety of names for the thing depending on what context you're in. But the idea is generally something like this. I have a set of data points that are at some time points, okay? Ti is for the time, and yi might be a vector, okay? It can be a collection. Okay, my camera is overheating. I should refresh it some way, find a way to cool it down. And whenever it considers it's too hot, it just shuts down. Okay, so what I was saying is the yi's can be vectors, okay? It can be a single data point, or it could be several with a value of several different state variables, for instance, okay, at a given instant in time. So the times belong to some interval of time. And then we look at, so here I'm looking at the SIR model, okay? And I'm going to say, well, the solution to my SIR model at time t is some t x of t. So SIR here, for all the times in the same interval of time that we're considering. The model parameters are p, and we want to minimize the error function, which is given by, okay, so these are the data points, okay, 1 to n are so there's n data points, and I want to minimize the difference between the TIs are the points at which we have information, okay, the data points are located. So x of ti is the value of the solution to the SIR model at time ti, for which we have the data points, and yi are the values of whatever we're comparing at the same times. The norm that we use is typically the Euclidean norm, but it could be different. I mean, you could think of, for example, you might want to minimize the error in terms of the maximum difference between x of ti and yi. Okay, but what happens is that, okay, you compute some norm like this, and given a point in parameter space, okay, so I take a point in parameter space, I'm going to compute the solution to the differential equation. That is going to give me the x of t, from which I'm going to extract x of ti. I'm going to compute the norm of x of ti minus yi, and I'm going to sum this, and that is going to be the error of that I'm making when I'm taking this point in parameter space, the distance between my solution that I get by using the parameters that I'm trying and the actual data points. And what I'm going to do is I'm going to try to minimize this error by varying p. Okay. So here, let me point out, so I'm not going to use the entire state space of the entire state of the system. I'm just going to use, so here typically we're going to have incidence, okay, and the data that I'll show you, I have incidence. That's going to be the number of new cases per unit time. So I need something that I can compare to that number of new cases per unit time. And remember, I have said here and there that when you look at an SIR model, I of t is not the incidence, it's the prevalence. Okay. But so how do I get incidence in my model? Well, it's quite simple. So if I have a mass action term, incidence is the rate at which new cases are generated per unit time. Okay. And so that is simply beta SI, or beta SI over n if I have a standard incidence. Okay. So if I'm using mass action incidence, what I want to do is I want to minimize this function. And if I have, so and here I'm taking the Euclidean norm, okay? And if I have standard incidence, I'm minimizing this function here. Okay. So this is going to be evaluated from the solution, and this is going to be evaluated where this is the data. Okay. So let me now switch to an R session. Okay, I have turned on RStudio, and this is in this course the first time I'm showing you this. So this is an RStudio window. Briefly, before I talk about fitting, let me just detail what is there. So first, here on the top left, you have you have the code window. Okay, this contains the different programs scripts that you have opened. The scripts are here. This is the command window. So this is an R session here. I could, so I've restarted. In principle, there shouldn't be anything in memory here. It also includes a terminal. So here, this is a Unix command window that's set in the same directory as I'm working. Here on the right, and it's probably too small to tell into detail, but we're not going to use it much. There's an environment window, which for the moment is empty. That environment window will have the different variables and functions and so on that you've defined in your command. I should go back to the command console. That you'll have defined in your console. There's also going to be a history, so if you need to rerun a command and you don't remember, you can search for history, etc. There's connections, don't worry about this. What's interesting is if you're working on GitHub, then there is a GitHub interface here, and the bottom, I'm not going to be using that one much, so I can forget about it. And the bottom right has a file browser, a plot window, a list of the packages that are in memory or that are usable, the help viewer, there's no help open yet here, and a viewer, which I don't remember what it does. Okay, most of the time you'll be playing with the files, the plots, the help that comes out here, and here the environment is typically where you will be looking. So here on the left, I have the code that I'm going to use to do the fitting. And let me explain what's happening. So first of all, here I'm listing the libraries that I'm going to be using for this program. And this is the right-hand side for the Kermack and McKendrick. Okay, so I have, I am using, and I'll point out, I'm using beta SI over N, because in this particular instance, I tried both beta SI and beta SI over N, and beta SI over N worked better. So exactly as I was explaining before for the logistic, but here I have three equations. You can see that the same. I'm using with as a list X, which contains S and I and R, P, which contains beta, population, and gamma. And so this is simply the Kermack and McKendrick model with proportional incidence. This one is when you're doing parameter fitting, this is a very important function. So this is the function that will return the error based on the parameter value that you're using. So I'm going to allow, this is where I'll put the parameters that I'm going to vary in my optimization routine. These are other parameters, if there's any. This is the data that I'm going to use, so the proper data. The method, this is to define what type of integration method I'm using. And also the data that I have has several columns. And so here I've made this additional argument that is simply what column I'm using in my data. That's the incidence per 100, but that's actually not the one I use, and you'll see that below. By the way, when you define a function, you can indicate a default for a value. So for instance, if I have written method equals RK4 like this, it means that unless I call the function error incidence with an argument method equals something different from RK4, by default it will use RK4. The same way, unless I call things with something else than incidence 100, then what it will use is incidence 100. Okay, so remember what this function must do, and that's probably oftentimes the most complicated too. I should evaluate functions as I go as well. So by the way, you can see I've evaluated the function, and now it appears on the right hand side in the environment as a function, so it's in memory, and I can use it from now on. So that function error incidence is probably the hardest one to create originally. So look at what I'm doing here. So remember I said p-vary is what will contain the parameters that I'm going to vary. And I'm going to vary beta and gamma. And I simply say, make a numeric value because it comes out with a name beta. So it just make purely a numeric. Make a numeric value from whatever I send you that's called beta and call that params beta. And make a numeric value from what I send you with gamma and call that gamma. Now, if you think about the problem, we are going to have an epidemic. And so, of course, we don't want to have our values of R0 less than 1. We know that if we find a value less than 1, then what the solution is going to do is it's going to decrease. Okay. And so to avoid this, what I do is I simply include a check of a value. So if I provide a value of beta and gamma that is such that the R0 that I get is less than 1, then I will return infinity. Remember, this is the error. So if I say the error is infinite, it's bad. Okay, I want an error that's small, and I'm returning infinity, so that's not good. Then I need to set the initial population, the initial conditions for the model. And what I do is, well, I set S0 to be the total population, but then I say that I0, and this is a little trick, so if you think about it, the initial number of infected in the population have to give me the incidence. So the data that I have is by incidence, okay? I'll come back to that in a second. But to get the initial incidence, well, all I need to say is that, well, the incidence is beta Si over n, therefore I of 0 has to be incidence times n divided by beta times S of 0, which, of course, n and S of 0 are essentially the same. So essentially, to begin with, if I divide the incidence by beta, that is a good value of I of 0. And this is what I do here. Okay. So then I set the initial conditions to the model to be S of 0, which is the total population, I of 0 that I just computed, and R equals 0. The times are going to be the times at which I have my data points, and I'll convert them to numeric because the ODE doesn't want you to use proper dates, it wants numerical dates. So this is simply the number of days since January 1st, 1970, and that's what is used, okay? But it doesn't matter because what's important is we have a good spacing, okay? The t equals 0 starts at one point, and then we have the good spacing between time points, and we output the solution at those same time points as the data that we have. Okay, so then this is the solution of the ODE. I'm doing some error checking because this problem is sometimes complicated numerically, and it happens that the ODE method gives up before finishing over the time that I'm asking it to integrate for, and if it finishes early, it typically means that there was problem with the integration. And what I'm doing in this case, I'm doing like I did before when the parameters are not good and are giving me an R0 less than 1, I'm also returning infinity. Okay, this is another way of saying, well, don't do that, because the algorithm that I'm going to use is going to try to minimize this error, and therefore when you return an infinite error, it's bad. Okay, so then my solution has S, I, and R through time, but to compute my incidence, what I need is beta Si divided by n. So I compute the incidence from the run by computing beta Si over n. And to compute the error, I just need to, and so this is where I specify which incidence function I'm using, so incidence per 100 or proper incidence or whatever, and I'm computing the difference between the two vectors. So this is the two vectors are the same length, and I'm computing the distance between the values of my solution minus, the values of my data minus the values from my solution. I square that. So this gives me the square of the differences, and I simply sum, and I return this, and that's going to be the error. Now let me show you getting the data. So this is data from a French surveillance system. So let me evaluate the function. So you see it's now appeared in the environment. So this is a surveillance system in France. So I've just downloaded the data as of current, okay? The data looks something like this. You have the output here, so there's a week. The indicator here is simply the number. This is the number of cases of influenza, I think. This is the incidence. So these are computed numbers, okay? So these are not, this is a sentinel surveillance system, so it's approximated numbers, but this is the numbers that they find by approximating. They have the incidence, they have low and high values of the estimates of the incidence for a given week. They have the incidence per 100,000 people. And high and low values as well. And what geography they're looking at. So this is the entire country and the geography name, which is France. So this is what we have. We need to do a bit of wrangling to make the data into something we can use. So I need to find what year, what week. And so if I go back to looking at the head of the data, in this case, of course, it's not going to show. I have, what I've done is I've split this information here into the first 4 digits of a year. The last 2 are the week number, and this is what I did here, okay? I'm also going to make dates, but there's some issues which I fixed by doing this because there are some in weeks. Oh, this is not because here. There's something with the way the weeks are numbered, where you end up with week 53, which causes issues in some cases. But anyway, this, what I'm doing here is I'm fixing this. Oops, I think I did something silly. Okay. So let me just arrange. Oh yes, the data comes, the latest point, the top point in the data file is the latest point. And of course, we typically look more at time going down than up. So here I'm simply using another function in the deployer, which simply says that I'm going to arrange the data by sorting on date, which is one of the columns. And here I'm going to use incidence to be incidence, okay, not per 100,000. So let me show you the data that we can work with. I'm going to work with the 2018-2019 flu season, which looks something like this. Okay, this is the data. I'm restricting it a little bit because if I had a much longer season, things come out badly sometimes, but okay, this is this. Though I'm dividing by the total population, so I need the total population. Let me get the most recent value of, actually, most recent value, I should have said 1 here. This is weird. Okay, but anyway, so I'm getting the data, and you can see that the data, while you're populating them, the values appear, okay, beginning year, end year, and population data of France is coming out here. Okay, and that's it, population data, 67 million. So we're ready to go. And so I make a list of parameters, which are not very important here because what I'm going to try to use as my fitting parameters are beta and gamma. Okay, you remember at the beginning of the error computing function, this is what I have. But I'm adding the population, total population, as an information. And now what I'm going to use is what's called a genetic algorithm. So there's plenty of ways to minimize things. It turns out that this particular differential equation is sometimes a little messy and doesn't work very well with some of the deterministic fitting algorithms. And so here I'm using a genetic algorithm. So the idea of a genetic algorithm is you make genes that consist in the parameters. So here my parameters are beta and gamma. That's the ones I'm going to change. And I make a gene with those two parameters. And I make a population of genes. So I'm going to actually make 500 of them here. And every generation, I'm going to compute the fitness of each of the 500 genes that I'm making by computing the error. But a genetic algorithm, the aim of the genetic algorithm is to increase fitness. Of course, that's like the organism with a better fitness survives. And so because we want to minimize, what we have to do is increase negative error. Okay, so this is a common trick if you have a quantity that you want to minimize, but the function maximizes, you simply maximize minus the value. Okay, so I'm going to maximize minus the error. And the parameters I indicate here, and you see I'm using the function as I was describing before. This allows me to use a function of several variables, but to indicate that x, all that varies is x here. Okay, all the others are fixed within the function, and what is varying is x of 1 and x of 2. The cool thing with a genetic algorithm, so first of all, you can parallelize easily. So this is saying use no more than 120 cores, because R has an issue with more than 124 cores. So if I use the 128 that I have here, there's an error. So I'm saying, well, use a little less. You can very easily set an upper and lower value for the value of the parameters you're looking for. So the first parameter is beta. I want it to vary between 0, 1, and 1. And the second is gamma, and I want it to vary between 1/20th and 1/2. You can set values for crossover and mutation. I'll let you play with that. This indicates that I want to use an optimization, deterministic optimization step from time to time that can help in fine-tuning a value that you find. These are initial guesses that I'm giving it, and I'm saying do 100 generations. And let's run this. So you can see it's speaking to you. It's giving you the, so the mean error is infinity, of course, because it's finding a lot of cases where our 0 is less than 1. And so it's neglecting those because clearly we have an epidemic. Okay, so I'm saying, yeah, just get rid of the R0 that are negative, that are less than 1, and just keep what is larger than 1. And so you can see that my error is quite bad. But of course, because if you're thinking about the numbers, these are large numbers, and I'm going to have errors that are going to be the square of those large numbers. But let's see what the solution looks like. So this is what our solution looks like, and this is what the data looks like. It's not great. Okay, as I said, there is no, I'm not saying this is going to work well, but it's okay-ish, okay? So this is what you see here. I should point out, for instance, in fact, I'm fitting here on the value at a given time, okay? In fact, I should use, because those values are the data points we have are over a week. So I should probably integrate the solution over a week. Okay, as I said, this is not a perfect method by any means. It's just meant to illustrate. Let me, so this is it for fitting. The code is available on the repo, so feel free to use it, modify it, whatever. Let me show you some other briefly while I have an R session open. Let me show you the source data that I was showing you earlier. So this is the graph that I showed you earlier. And two things that I want to show. The first one is a Shiny app. So we were discussing a little bit earlier what is a Shiny app, and let me illustrate this. So you have to include this is not CTM CSIS. I should remove this. So a Shiny app, it takes the name app. You won't see it here, but it's in here. It's in Erlang Shiny. Typically, it's best to have it in a subdirectory because it's best if it's called app. Although now I think, no, I'm saying something silly. I think now you can call it whatever you want. RStudio will recognize. One thing that you might not see well here because of the resolution is that when I switched over from my code to the app, there's a button that appeared here that's called Run App. And let me see. What happened when I clicked Run App is that this window appeared, which is the one you saw the other day. Let me make it a bit bigger. In one of the that you saw the other day or not. When you will look at the lecture 6, you will see this this running within a web page. But this here runs in an independent window, and what you have is code that is, oops, that's not what I want to do. I want to be here. That is going to be reactively evaluated as you change parameter values. You can see that the output that we get changes as a function of the changes here. And okay, so this here, so let me go back to no, that's not the one I want. Okay, no. Did something silly. Yes. Okay. So the code here is quite simple. You end up defining, you have things to define, for example, the sliders. And you can see that here I'm taking a slider that I'm saying the variable that's tied to it is mean expon, and then it's described by mean of the exponential. I give it a minimum value, a maximum value, a default value. The same way the number of compartments, minimum, maximum value, and a step if I want. And then in the, so this is what is called the page itself. And then there's a server side that takes whatever is happening in your page and transforms it into, in this case, a plot, well, two plots. And our studio, but Shiny makes it so that the thing is interactive. And another thing that I want to show you very briefly is, so I'm sorry, this is in French. I've included it also in the code directory. This is a talk I gave in Dakar, in Senegal, just like 3 months before COVID. And I've simplified it here, but this is R Markdown. So this is another feature that is really nice of R. And so let me show you what this is doing. So this is the sort of a header. It's defining the type of output that you want. It's in the subdirectory R Markdown example, by the way, here in the code. It's saying that it's a Beamer presentation. Shanghai is a Beamer style that I defined, that I edited, and so it will look for this this style, which is here somewhere. Probably not able to see, but it's in the subdirectory R Markdown example. It uses an in header to define some LaTeX things. And then what you do is you write those chunks of R code, and they're separated by three little back ticks. And then you say it's R. You can give it a name, like the code chunk has a name. So this is just setting things up. But you can see, so as I said, sorry, this is in French, but here I'm writing slides and I'm using Markdown. But then in the Markdown at places, I'm going to, so this is all regular Markdown, but here, for instance, what I did, the example of the population of South Africa, I did that time with the population of Senegal. And you can see that here I have an R chunk and it appears as slightly gray. Okay. And what is happening here is that I'm using WB, what we saw before. Actually, I'm here, I'm using the data that I've downloaded, but I could use the online version to make this plot of the population. Or here, these were things about the Dutch elm disease. And here, for instance, I'm getting the data from the city of Winnipeg, and then I'm just saying these are the number of elm trees that you have, and this is the number of trees that I have, and in total, if I sort out which are American elms, then I will have a certain number. And then here, in reaction to me having opened a file that has extension RMD, RStudio pops out this knit thing here, which you can specify options for. So for example, you would want maybe to make HTML instead of PDF, but I'm going to make a PDF, a beamer. Okay, and by default, that's what it will do because I've indicated it's a beamer. It's now compiling. So the first step is that it runs all the R code that is in the program, in the script. It can take some time. So right now it's probably downloading the elms, and then it generates a beamer file, LaTeX file from the code. And eventually, when that happens, so you have to have LaTeX installed, of course, if that is going to work. I don't know if it's done. I can't understand. I think it's done. Okay, there's a PDF here. Let me, no, I'm not able to open PDF, so it's still running. Okay, of course. Why is it doing shiny? It shouldn't be doing shiny. That is bizarre. Okay, let me, no, I don't want to terminate. Okay, let me terminate and restart. Okay, so let's go the fitting. Okay, why is fitting empty? That's interesting. Control Z. Ooh, something weird is happening. But let me see if this runs. Okay, so let me try knitting this. I have to make sure that I don't save the empty fitting. So when I'm talking about this, as I said, the chunks can be named. It's a good idea to name them sometimes. This way, when it's running, you can see instead of a named chunk, it will say whatever name you have given it, which is useful. It has compiled. I just need to change my input. Okay, I have no clue what's happening here. But okay, in principle, what you should see is not an empty window. You should see a PDF that you can find in the R Markdown example subdirectory of the code. And that PDF is a Beamer presentation that has included but in which the code that the R code that I've included has run, and the PDF has been generated. And that's very useful if you're going to generate reports on a regular basis about something that evolves. So for example, I was using this during COVID. Data is generated daily. I wanted to run some basic analysis of some of the data daily. Well, I could do this by just regenerating a report every day. And that's it for this.